Now in this video we'll solve the first question of the class 1, where we are asked to consider a linear model yi equal beta 0 plus beta 1 xi plus ui, and here it asks we have to estimate beta 0 and beta 1 by minimizing the sum of squared errors, and ui is basically errors. Now, sum of squared errors, let's define a function for sum of squared errors. That function is s of beta 0 and beta 1, and notice this is of beta 0 and beta 1, so these are the unknowns in this case, equal sum of, so this is 1 to n, yi minus beta 1 xi minus beta 0. Oops, I just misplaced them. Should be fine. Square. So this is basically sum squared errors, and this is basically ui here. Now, and if you remember, minimization technique is actually an optimization technique from your calculus classes. So now for this, we have to take derivative of s with respect to b0 and then beta 1. So let's do with respect to beta 0 first. So delta yi over delta beta 0i, so this is a hat here now, I'll start putting hat because it's an estimate now, is equal to, when you take the, using the chain rule, when you take the derivative of this function, you get the 2 here, right here. It's always a constant, and it's a constant and always outside. It should be before the summation sign now. Well, I could put it here and then show you how it works, but you know it from the summation operator video from before, so I'll leave it as this now. So yi minus what we have inside stays the same, xi, so this is hat now, minus beta 0. I have to change this now to in the right way. I mean, it should come here to beta 0, should be before beta 1 hat xi basically. Next, and when you take derivative inside the function, inside this bracket, you have to take derivatives as well. So when you take derivatives with respect to beta 0, you will have then minus 1 here and equate it to 0. Now divide both sides by 2, minus 2, let's say. 1 to n yi minus beta 0 hat. So this is beta 0 minus beta 1 hat xi equal to 0. Now let's use the first distributive rule of distributive rule of summation sign, which leaves us with a nice simple formula to work with. Yi minus beta 0 hat minus, now beta 1 hat is a constant, so it will be written before summation operator, xi equals 0. Next we do a little bit of simplification here. This will stay the same, so let's write it down. Minus. Now the sum of the beta 0 hats are basically n times, so n times, oh well, sorry, we're basically summing n of these beta 0s here because the summation runs from 1 to n. So simply it's 1 times beta 0 hat from the first rule of constant in summation operators, minus, nothing changes here. So this is 1 to n equals 0. Next, from this point onwards, we can now work out what beta 0 hat is. So let's put this term and this term on the right hand side of expression and equation, and then divide by n both sides, well, minus n. Then what we'll have is this here basically. This is 1 over n now because I'm dividing by 1 over n, minus 1 over n. This would then be minus 1 over n, 1 to n xi. And sorry, beta 1 hat is missing there. From here now we know this one is y bar, So because that's basically sum of y divided by n, there are n of y's, n, so that's sample mean. This is not anymore y, I, because it's a sample mean is a constant. So let me clean this quickly. Brain started malfunctioning a bit. So next we'll have the beta 1 hat here. Now this whole expression is basically x bar now, because this is here is the sample mean. So the result is this. So we have to keep this in mind because we'll use this in the next few steps. So beta 0 is equal to sample mean of y minus beta 1 hat, estimate of beta 1 basically, times the mean sample average of x's. Now let's take the derivative of this s function with respect to beta 1. For this I'll just clear the space so that we can have more space, because we need more space actually for this one. It's a bit bigger. Now I'll directly start I'll just start from the first order derivative of s with respect to beta 1, rather than just showing you how to do this and what to do. You could figure this out yourselves. That's an easy part. When you take derivative with respect to beta 1 of this s function, you will have 2 yi minus beta 0 hat minus beta 1 hat xi times, here when you take derivative with respect to beta 1 hat, this expression becomes xi negative xi, basically, because there's one sign there, equals 0. Now let's divide both sides of the equation by -2. We'll have this expression now. Oops, this is not beta 1, it's not beta 0 anymore. Xi equals 0. Let's now multiply in xi's and use the distributive rule of summation. This would give us 1 to n yi xi minus, now beta 0 is a constant, so it's before the summation sign, xi here. Notice that I'm multiplying in the xi's and at the same time using the distributive rule of summation. Beta 1 hat is a constant as well. We'll have now xi. So there are two xi's. I mean, well, when you multiply them, this would be squared. That's the result. Now, what to do next? I have betas, which are unknowns. They can be put on the one side of the equation, so let's do that. Let's bring this to this side, then replace beta 0 hat with the result from the earlier results for the beta 0 estimation. So if you remember, it was y hat, so basically beta 0 hat was equal to y hat, sorry, y bar minus beta 1 hat x bar. So we'll basically plug that in as well into this equation. yi xi equals, now I'll just do this substitution here. So this will be y bar minus beta 1 hat x bar. So notice that I just substitute beta 0 with this expression here, times the xi here, 1 to n xi plus beta 1 hat xi squared, 1 to n semicolon. Now let's work with this side. Here I need to do some simplification here. So y bar is basically 1 over n times 1 over n times sum of y's, and x bar is a similar way, it's 1 over n to xi's. So the result would be then yi xi equals 1 over n y's So this is the sample, basically this is the sample mean, which is y bar here. Then here beta 1 hat 1 over n sum of xi's originally, plus beta 1 hat, we'll leave that expression as before, xi squared. Now let's multiply sum of xi's in, and let's see what we can do further. 1 to n yi xi stays the same. Here we'll have 1 over n, well, xi times yi minus beta 1 hat 1 over n sum of xi. So this is basically squared now. Sum of xi times sum of xi is the square of the sums basically. Plus we'll have beta 1 hat 1 to n xi squared. Now we can do something here. So we have now beta 1 hat, and then we are in a position to work out what it is. Now let's do further simplification here before we can go forward by, let's say, converting this into x bar, this one into y bar, so that it's easy to work with constants, and then, well, we can do some conversion here, and then we'll see how it goes. Let's have a look. This one, I think we can leave it for now. We won't be able to do this, convert this into proper constants, not anymore. So let's leave it as it is for now. Maybe later at some point we do that. So what we have now, let's skip this one and put this one into this side, and I think I can do the transformation directly here. This would be now, if this would be x bar, right? This would be x bar basically. Times, this would be, if I divide this by n, multiply by n, I will not lose anything. So basically this would be y bar times n. So I'm not losing anything in this case. Equals, here, well, this will be beta 1, so I'll just bring this forward, this expression here, because this one has a minus here. xi squared minus beta 1. Now here we can do something, I think. 1 over n, let's change this to this 1 over n times n. Well, let's not write it that way because it gets confusing, I think. Let's do this. I multiply this expression inside the bracket and divide it by 1 over n, multiply it by n, divided by n, xi squared. Right, so what we will have now is, if I rewrite it again, minus x bar, y bar, n. Now this will be staying the same as before, minus, here now basically this part here becomes x bar. So this is basically average of xi's, 1 to n here. So n times x bar, I can take this n out of the bracket. This would be n squared over n gives me just n, so I'll have then beta 1 hat times this n times the x bar squared now. So that's much simpler. Now from here we could now find beta 1, what the beta 1 is. So basically beta 1 is then, if I take it outside the bracket or factor it out more appropriately, this would be 1 to n xi squared minus n x bar squared equals, so I'm swapping now the places, the right hand side with the left hand side, it won't change much. This would be 1 to n yi xi minus x bar y bar n. and from here beta 1 hat is basically equal to, now this is n 1 to n yi xi minus x bar y bar n divided by n here xi squared minus n x bar squared. Now, well, this is the result, this is the final result, but if you look, we could actually do some more changes, and it's a bit difficult formula to remember as well. Now what we can do here, let's rewrite this formula in a new space. I think I'm constrained by the space here. I may not be able to write all of this and next few steps in here. So let me clean this. So take a note that this is the result as we had in the class as well. So let's clean this up. Now let me rewrite what we had for the beta 1 estimation. So we have beta 1 is hat equals to, well, it's slightly dense here, so yi xi minus n y bar x bar over sum of xi squared minus n x bar squared. Now I think we can do simplification on both of these, numerator and denominator. Let's start with the numerator first. This would be 1 over n yi. I'm just copying this again. Y bar x bar. Now let's do a simplification. A little bit simplification gives us some flexibility. So let's expand this. I mean, let's plug a formula into this, the formula of the mean. So this will be 1 over n y, sum of y's basically, minus n times 1 over n. So I'm expanding y bar, yi's x bar. This would give us, this will stay the same, xi, this times here, minus, now you get this ends cancelling, have yi x bar. Now using the first, well, I keep saying first distributive rule, it's the distributive rule of summation. I can rewrite that expression like this here, minus yi x bar. So these two expressions are equal or equivalent, and then I can see that yi is common in both of these expressions, so I can factor it out. Then this will be xi minus x bar. Now this should remind you something from our yesterday's or from previous video where we said that this equation, this expression would be equal to, actually we proved it, to this expression. So this is xi minus x bar yi minus y bar. So this is something that we proved yesterday. Now to find how this is equal to, how this works in this form, you can watch that video, or I'll just do a reminder to you. Now this thing here, from, assume that this doesn't exist here, we didn't write it. So from this point on, we could write this actually in this form: yi xi minus x bar. Now we can do this by minusing something here. That thing will be 0 basically, and that 0 was this, if you remember, y bar xi minus x bar. Remember this? Well, this part here is basically 0 because this is deviation, sum of deviations, and we proved also that sum of deviations is equal to 0, so we are not losing anything by writing this simple expression into this form. So ignoring that this is equal to 0, we can multiply this in this y bar in, and then open the bracket multiplying this yi in, and then using the distributive rule you can work out that the whole expression would basically be equal to this nice expression. So we'll not repeat this exercise again, so you'll do that. So let's now plug that in. So basically this would be from here this implies basically the numerator will be then xi minus x bar times yi minus y bar. So that's the simpler expression for the numerator. Now let's simplify the denominator and what we get here. Okay, let me write this in a slightly different color, maybe in a red color, so that we know what we are doing here. This is for beta, sorry, it's for the denominator. Now denominator is basically, I'll rewrite this again to keep track of what we are doing. So this is x I squared minus n x bar squared. Now what is this equal to? Now let's expand this here. So what we'll have, in other words, we will just plug in the, well, basically this is a square of the mean, and mean will just put the proper formula for the mean would be 1 to n xi squared. So that's what it is equal to. And what we'll have is this expression here. So this is I minus, now 1 over n comes out of the bracket as 1 over n squared, and one of the n's will cancel out with this n here, so we'll have 1 over n, simple 1 over n, times the sum of xi's squared. Now what comes out of this now? So let's give it a few seconds of thoughts. What can we do here? Well, we could rewrite this in this form. So let's start here. So this is xi squared minus 1 over n. This is basically xi here times xi. So I just factored them into two terms here. Instead of saying sum of the x's squared, I said sum of xi times sum of xi. So this would be the same as sum of xi squared. And here what we see is this term here is basically an x bar, isn't it? So then xi squared minus x bar xi itself. And now it's getting a bit congested here. Now we can use the first distributive rule here by writing it this way, rewriting this whole expression into a nice manageable expression, squared minus x bar xi. Oops, I think I shouldn't have done that because summation operator is already there. So this would then be xi here. Now a common thing here is the xi in both these terms, so we'll take the xi out of the bracket, factor it out basically, and we'll have xi minus x bar, right? And this is 1 to n. I ignored them here. I guess this doesn't actually make much difference. So summation runs from 1 to n, xi minus x bar. And if you remember, this simple expression can be more simply written in this form. This is 1 to n xi minus x bar squared. So sorry, now this is again from my first exam, first video on summation operators, where if you expand this expression you end up having this basically. Or you can we can do it the other way around, start from here and come to this point by manipulating this expression algebraically. But we don't have time for this, already 25 minutes, so you get bored probably to do this, but I'll leave it to you to prove that this expression equals this expression if you do not want to watch the video I made for the on the summation operator. So let's write this result here. So, well, they're getting interesting now. This is 1 to n xi minus x bar squared. Now this is the OLS estimator for beta 1 hat, and that's the answer as well for this question 1. And it took me half an hour to do this. I think we can manage with half an hour time of your time. Yeah, I will try to do now next question, number 2.